Welcome to the machine learning track, and I'm your host, Priyanka. Let's begin the session. We know that machine learning can do wonders when put into application. Then, how can machine learning leave the marketing field behind? In our upcoming talk, the intuition behind machine learning in marketing will bring forth key insights on how AI or ML is useful for marketing. Let's demystify this core technology with interesting case studies with our next speaker, Maria Vinasco. Mario Vinasco is a director of analytics at Credit Suisse, and he has previously worked with Uber, Facebook, Google, to name a few. So this is a pre-recorded talk, and I will just play it for you. Enjoy the talk, and I'll be right back.
Good afternoon, attendees of the Big Data Europe Conference 2021. I wish I could be there in person, sharing this great conference with all of you. And as countries and borders get reopened, hopefully we'll get to be there very soon, sharing these interesting experiences and projects. Today, I'm going to talk about some use cases in machine learning as it gets applied to marketing analytics, specifically some of the intuition, some of the key concepts of these very key and powerful technologies that we now have at our disposal and can be used for our day-to-day decision-making in attribution, causality, segmentation, cross-sell, and many other things. I am Mario Vinasco, Director of Analytics with a fintech company called Credit Sesame in San Francisco, California. And we are going to share some of these use cases, as I mentioned before. I'm going to give you a very brief introduction to what machine learning is, with the purpose of driving those concepts home and really nailing them down. And it's going to be very brief into that. We will then move into what models we use in marketing, some of the models, some of the best practices, if you will. And most of the time we'll be spending in the use cases presenting in this. A few years ago, the state of the art in machine learning was computer vision. Today, this is one of the most trivial cases that we have and is taught in introductory classes to grad students, to undergrad students. By now, we all know computers can do this. In 2014, as I mentioned, it was extremely difficult for computers to be able to correctly, or at least at human levels of accuracy, to classify photos of cats and dogs, for instance, or any other thing for that matter. Several things happen that make this possible, and now it's an absolute trivial exercise to do this. Obviously, one of the first tricks that need to be applied is how to convert these images into numbers. Computers do not understand textures, colors, or shapes. They do see and understand numbers. One easy trick to do that is dividing the images into 200 pixels vertical by 200 pixels horizontal. There you have 200 times 200 is 40,000 pixels per image. And if each one of those pixels gets represented by the amount of red, green, and blue, now we have three additional dimensions. 40,000 times 3 is 120,000 numbers that the computer understands and represents each one of those images. We train the computer in thousands of those images, and now you get an idea of how difficult was this before the computing power that we have now, because the numbers quickly escalate in terms of the times that it takes to do this. You feed that through what is called a perceptron, which most of you already know by this, but the point that I want to make is that this is a very simple mathematical operation in terms of a sum product. You multiply the numbers x, which represents each of the values of the pixels, times a number w. You sum them up to produce a 1 or a 0, depending if the photo is a cat or if it's a dog. The number w's are unknown, are the numbers that the computer needs to learn, needs to calibrate or guess. Therefore, the name of machine learning. Obviously, a simple perceptron will not do the trick, but when you stack many of those perceptrons and many layers of those perceptrons is when the magic of machine learning, the magic of artificial intelligence happens. Again, in 2014, this was a state of the art, and it had been difficult, even for me, let's say, 7, 8, 9 years ago to believe that a computer could achieve the levels of accuracy that humans have at recognizing these images, but we know that now that is completely trivial. Why am I telling you this? I am telling you this not because we are in the business of classifying images or classifying cats and dogs, but because we are dealing with customers that continue a subscription, customers that churn, customers that can purchase additional products and services from our companies, cross-sell for that matter, or attribution to investments in digital spend and how my KPIs move. Imagine that instead of having the cats and dogs and the 120,000 pixel values per photo, what we have is customers, how many times they log in via the app, how many products, financial services have they applied to recently, how many complaints they have. In the case of Uber, for instance, my last employer, in the case of the drivers, how many kilometers and how many trips they take in a typical day by day of the week, how many complaints and incidents with passengers. You get the idea. The idea is collecting a lot of behavioral data, a lot of data that can be predictive of future behavior, or at least strong correlations that we can exploit for this. Imagine then you collect 50 or 60 or 70 data points or features, as we call it. You train a neural network into that data, and this is past data that you know that what happened in the past, meaning that if this is a churn model, for instance, and you take a look in the past, you know of all your customers who truly churned, who truly abandoned your platform, and who stayed, and you know this behavioral data. And you train them, and what the model produces is a set of probabilities that the customer, based on the correlation observed in the past data, is going to churn in the future. Now you take your existing customer base and you score them through this model. The model again produces probabilities from 100% to 0% that this customer, let's say in the next 30 days or so, is going to churn or abandon your platform. You have to make a call, or you have to make a threshold and say, above this line, I am going to assume, or I'm going to predict that these customers are going to churn, and anyone that has a probability below that threshold is not going to churn. Remember, this is my existing customer base. I don't know yet what is going to happen with them, right? I'm making this prediction. And notice that I use classification in the case of the images of cats and dogs, and now I'm using prediction. The meaning is the same. Prediction is when I look to the future, I know when I look at instances that I have not seen in the past. If I wait 30 days, if the model was trained for 30 days or 60 days for that matter, what I will see is that indeed, some of the people that I predicted, or the model predicted that was going to churn, they indeed churn. These are what we call the true positives. But you notice as well that we have some false positives, and that we miss some people that indeed churn. In marketing, it's very common to see the total accuracy of the model, meaning the percentage of time that the model is correct in the 75, probably 80% is the highest that I've seen. Then you might ask, why would a model with only 80% or 75% accuracy would be any good? After all, you would not board an autonomous car with a 75% accuracy, right? You would not do that. In marketing, however, that's pretty good, and that's actually very useful. Let me give you a quick example. Imagine that you are going to design a campaign or a program or an incentive to prevent churn. Imagine that your churn is 10% per month, just to make things easier. Meaning that if you target randomly 100 of your people, of your customers, just by chance, you will catch 10 of the true churners. But you have to pay for 100 incentives, or 100 messages, or 100 impressions, etc., to catch those 10. Now I run the model. I rank my customers. I take the two top deciles, meaning I take the top 20% of my customers according to the predictive score. And in that 20%, I catch 5 or 6 of the true churners. So now imagine that instead of targeting 100 to catch 10, I'm going to target only 20 to catch 5 or 6. We are talking about a 5x or 6x improvement in the marketing efficiency. Sure, we are going to miss some of them, but so does the other model. And that's why we invest in these models so much, because of the usefulness that they have, because they allow me to be more efficient in my decisions and my investments. Now I'm going to share with you some of the case studies where we have used this, now that I have drove the point of the intuition, as I mentioned in the earlier talk, about using this metric, the recall metric, and how we use that creatively to solve other interesting problems. Let's start with the first case study in marketing analytics, where we perform an attribution exercise to understand what interventions of the many ones that we did in our customer base worked, and by how much, using precisely machine learning. We started this program in December of last year, where the marketing team was trying to acquire new users for our new banking business, new banking subscriptions, specifically trying to users to get to fund their accounts, deposit money. We did many interventions in terms of Facebook retargeting, mailers, incentives, $10 for depositing, $20 for referrals, sweepstakes, and many others. Several campaigns, several initiatives. We saw an overall lift in terms of the user that actually funded their accounts, but we didn't know what to attribute, what was working and what was not. Some of those campaigns were A/B tests, which is the gold standard for experimentation on causality, where you have a control and a test. The only thing that changes is one of the variables, in this case, one of the interventions, so you know if the intervention, that particular one, is working well or not versus the control. But we could not attribute any lift to any combination of interventions. Which ones were helping, which ones were detrimental, and by how much. We decided then to train some models because that's what we know how to do. We have data. We have a large user base that receive all these different combinations of marketing interventions, as I mentioned, mailers, emails, in-app messages, and many things. And the good thing about that is, by being disorganized as a side benefit, we have variability, meaning not everybody receives the same things. Some cohorts receive some combinations, some other cohorts receive some other different combinations with some overlap. That is a very good opportunity to train a model to learn on those differences. So again, I keep referring to the cats and dogs exercise. In the case of that was pixels. In the case of the drivers for Uber or the subscription was behavioral data. In this case was the daily different interventions that these people received and what was the overall response. So we trained some propensity model using this, some behavioral data as well, and the presence of the observed marketing interventions. As I mentioned before, these models have the ability to learn the weights, the correlations, or in other words, the effects of these different interventions by correlating the observed data to the actual outcome. We knew at the end of all these interventions who had signed up and who had enrolled, who had funded the account, and throughout the variability on the hundreds of thousands of people that we targeted with these interventions, we could learn how those combinations work. Again, what the model learned was the relative differences of when one thing is present or the other is not, and what combinations, what correlates well with the final outcome. We use this learning to score the users under different possible scenarios. As I mentioned, not everybody received every single intervention, but we could simulate once the model learns the importance or the weights of each one of those interventions. Again, Facebook retargeting, the mailers, the emails, the in-app messages. We could simulate the existing user base. What if I had sent, in this case, Mario, all these different interventions? I could simulate all the combinations. If we had 5 marketing interventions, that will be at 32 different scenarios, meaning I have one of them, none of them, all of them, or anything in between. Those would be 32 scenarios. So under those 32 scenarios, I could score all my users, meaning that in my case, for instance, if I were a person that was targeted by these interventions, I would have 32 probabilities or 32 propensity scores under each one of those scenarios. And that will allow us to decide for each person which one was best or which was best or what combination was best in average. The problem with most propensity models and the problem with machine learning in many cases, like in subscription, in churn or cross-sell, is that the distributions are highly skewed, like the one that you see in the screen, meaning that many people get a score towards the lower bands of the probabilities, and very few people get very high scores. Again, that relates to the fact that in marketing, we only have 75, 80% accuracy, meaning that the models don't necessarily pick up all the signals. And in this case, the total accuracy was even lower. But we can see that for some people, the predictions are very strong. That's the long, thin tail that you have there. When you plot the probability, when you plot the distributions for each one of the 32 scenarios, how do you know which one is best? How do you know if Facebook plus sweepstakes was better than the mailer plus the $10 incentive plus the in-app? How do you know on average if that is better? You cannot really compare these distributions to one another, or you cannot really take a simple average because that will be highly skewed. And this applies to many other things in life. What you observe is typically that very few people do a lot of things and most people don't do much. That's a common law. It's called the power law. And that's what happens here. And if you take an average, that is going to be highly skewed. However, in statistics, there are several tricks, several mathematical tricks that people that were very smart created for that. Something called sampling with replacement solves those problems, eliminates the skewness, eliminates some of the problems comparing that, and it translates those distributions into very nice normal distributions by sampling with replacement lots and lots of times. So this is a simulation where you will just take samples from the scenarios until you calculate a true average of that. And then now we can rank, and then we can put from highest performing to lowest performing all the combinations. So again, what does it mean? What is the yellow on top and what is the blue on the bottom means? Those are the relative lift in terms of funding a bank account, the average lift when you apply a certain combination of interventions. This allows us to quantify not only each combination, quantify not only each intervention, but the combination of those interventions, and focus and reallocate money and efforts to the best performing and defund or deallocate from the lowest performing. Again, we started with a marketing problem. We started with incentives, campaigns, messages, money, and sweepstakes. We didn't know what happened. We trained propensity models to understand what was the correlations between all the interventions, behavioral data, and the final outcome that we knew what happened, and use that to rank in this case. Another very common use of machine learning models in this case was cross-sell. Cross-sell, we did this. This was a project that we did at Uber, where most Uber Eats were coming from the Uber rides, meaning that if you take a ride or a cab or a passenger, you are more likely to order Uber Eats. But by how much? So what we did was we trained a model for cross-sell to understand the propensity that someone will have to convert to Uber Eats. What we see here is that in the vertical axis, we plot by groups, by cohorts, the probability that they converted, meaning that you can observe. If you observe in the past and historically, you observe that certain groups of people convert at very low rates, or what people convert at higher rates. And in the x-axis, what we have is the predicted score or the propensity that we calculated. Notice a big discrepancy here. Notice that when the prediction score is 70%, 80%, or 90%, it doesn't mean that these groups are going to convert at 90%. You observe that the actual conversion rate doesn't go higher than 14%, right? But what is very important to notice here is that even if the model is off, right, we can identify 3 clear areas where the model segment the audience, meaning that when the prediction score is very low, let's say 10, 20, or 30%, indeed, the actual probability of conversion to what is the actual probability of cross-sell is very low. It's no more than 0.5, 0.7%. When the prediction is high, the conversion is also very high. It's not 80 or 90%, it's 14, 15%, but it's 15 times higher than the lowest conversion group. And that's what is important, that relative difference. When the prediction tells me that a group of people is going to convert at a very high, with a very high propensity, they indeed convert with much higher rates than the other. And in this case, the left group converts at 1%, the right group converts at 14, 15%. That's a 15x difference. Thanks to the model, I am able to separate, segment, and understand that. And now the conversation becomes very interesting with the people in marketing or the people in product. What do we do about this? Do we focus on the high conversion people, or are they converting in good rates organically by themselves or with very minimal incentives? Do we send the most expensive incentives to the people in the middle, right? To the people right on that fence? Or do we keep accelerating the people that are converting very high? Both hypotheses are very valid. One thing that is clear is no matter what we do, the people that are in the left portion of the screen, the people in the low prediction scores, they are not going to convert no matter what you do. So why spend incentives? Why spend money? Why spend efforts on those people that are not going to convert? That's one clear insight that we can derive from that. And then the other discussion is open. What should we do? Should we accelerate? Should we put efforts in the people for the people in the fence? That's one case that I wanted to share with you about machine learning. And I'm going to share next another case where we use cohort analysis, also using artificial intelligence, specifically machine learning, to do that. The second case that I wanted to share with you this afternoon is cohort analysis, which is a very powerful technique to analyze customers or any other entities that share a common attribute. For instance, customers that sign up over the same week, over the same month, or customers that share a certain characteristic. For instance, they have the same credit score bands. For Uber drivers, drivers that drive in a particular region and sign up during a particular time frame. It is a common technique and powerful, but with the help of machine learning, this analysis, this technique can get even more powerful. Specifically, cohort analysis is very commonly used across many industries and across many other projects. Users that share common characteristics, as I mentioned before, and the most common ones are cohorts by time of initiation to certain event. When you draw the curves by cohorts, the common characteristic that they have is the number of days since the event happened, not calendar days, because I might have registered last week, you might have registered this week, but the next day for me, regardless of the actual date, is day number 2, day number 3, and so on and so forth. What makes these curves, cohorted curves, very powerful is that they tell us not only the saturation level, meaning at what maximum level they convert. For instance, if they sign up for a banking product, what is the funding rates that they received? If they register for our platforms, what is the revenue that they create? And so on and so forth. And then you can see that many cohorts behave very differently. So the curves show us the level at which they saturate, as well as the number of days that it takes to reach that saturation level. Therefore, you can design experimentations, not or incentives or interventions that not only raise the level of saturation, but also accelerate the number of days that it takes to get there. And again, the number of days that you see in the x-axis are not calendar days, are just number of days since the event happened, regardless of the actual date. So the next question is obviously, how do you choose this? As I mentioned, the most common way to choose that is by time of a particular event, time of the registration, users that registered in August of 2021, or users that registered in September of 2021, or the weeks of the month, or so on and so forth. Another trick, which is very powerful and proved very useful for us at Credit Sesame, was to cohort people according to the main features or the most important features according to a prediction model. Remember the cats and dog example that I keep bringing up to this conversation? Well, when you train these models, a byproduct of the algorithm is the importance feature, meaning that it prints a bar chart like the one that you see in the screen, telling you which are the most salient, the most predictive features to identify a certain class of items. For instance, in the cats and dogs example, it will be perhaps the colors and the values of the centers or the pixels in the center of the screen. For the Uber drivers, it was the number of incidents and the number of trips that they took in the wrong direction opposed to home at the end of the shift. At Credit Sesame, for instance, is credit score, like in the United States is a credit score, or the number of days they've been using the app, for instance. So when we cohorted by the most important features according to the predictive model that we have, we got double the usefulness of these curves. We could create these curves in ways that were non-intuitive and ways that were much more informative and much more insightful. And again, because the predictive model is telling us what is the score of these people and what are the most important features for that score, we obviously can group them or cohort them in that way and measure those curves that way and design the marketing incentives or interventions that we need, again, to raise the saturation level as well as to accelerate the number of days that it takes there. With that, I thank you very much for your attention. I invite you to read, communicate with me, connect with me to continue the conversation. Again, I hope that next year or the next event will be there in person, because these events get very fun and it's very interesting when people actually ask live questions and I can see the reactions from them. As we know, economies and borders are opening, and very soon I will have the pleasure to be there in person. Thank you very much, and don't hesitate to communicate with me, connect with me, and send me your questions. And I hope that these insights, these practical case studies that I mentioned today using machine learning, and again, the intuition, some of the ideas behind these models and how they can extrapolate it to, in my case, to marketing analytics would be very helpful to you. Thank you very much to the organizers for the invitation, and until the next